second speaker for this session will be Karthick Babu from ISI Bangalore, who will speak about discrepancy estimates of generalized polynomials.
Thank you, sir. I'm thankful to the organizer for this opportunity. Today, I'm going to talk about discrepancy estimates of generalized polynomials. So the theme of this talk is to study the behavior of fractional part of n alpha in the closed interval 0, open 1. So more generally, for any arithmetically interesting sequence kn, we want to study the behavior of the sequence of fractional part of kn alpha. So this sequence most likely like squares or kth powers or primes or square free like that. Those kind of sequence we want to study the fractional part of those kn alpha for on closed interval 0 open 1 actually. So there is often remarkable difference between rational alpha and irrational alpha. So first we see the case for rational alpha. So say alpha is p by q, be a rational number. Then by division algorithm for any np we can write a plus rq, where a is remainder of the, when we divide like by q we get remainder from 0 to q minus 1. So there are like only q many a's possibilities of a. So when we take fractional part, then it will be like fractional part of n alpha will be a by q. So alpha is, so therefore when alpha is rational, so the fractional part has only finitely many different terms. But the case of irrational is different. So in fact, so for n not equal to m, the fractional part of n alpha and fractional part of m alpha cannot be equal. Suppose they are equal, then we can express alpha as a fraction of two integers, which means that alpha is rational, but we pick alpha is irrational. So the fraction, so in that when alpha is irrational, the fractional part of n alpha, all the terms are different actually. In fact, Dedekind showed that, Kronecker showed that fractional part of n alpha is actually dense in closed 0 open 1 when alpha is irrational. So this, by definition of density, this actually says that, so if we choose any interval close to a open b, that particular interval contains at least one n. So there exists at least one n such that the fractional part of n alpha belongs to that interval actually. So in fact, more stronger assertion is true for this case. So this was proved by Hermann Weyl. To state the result of Weyl, we require the following definition of uniform distribution modulo 1. So given a sequence of real number, we say that this particular sequence is uniformly distributed modulo 1 if we pick first n terms of the sequence and take the fractional part, and we see that how many of them belongs to the given particular interval a comma b and divided by n, then that particular limit is going to the length of that interval. So if this happens for all the intervals or all the subintervals of closed interval 0, 1, then we say that that sequence is uniformly distributed modulo 1. In other words, so we can see that, actually the length of the interval is actually relative size of this particular interval in closed 0, 1. So in intuitive words, so the uniform distribution modulo 1 is equivalent to saying that the proposition of fractional part of that sequence contained in any given interval closed a, b approaches to its relative size. So then actually, so by Kronecker, we know that the fractional part of n alpha, so given any close to a open b, there is at least one fractional part of n alpha, but Weyl showed that it is actually uniformly distributed. So therefore, it contains as many fractional part as relative to its size of the interval actually. So in fact, Weyl proved much more general theorem. Given any polynomial, real valued polynomial, polynomial with real coefficient of degree bigger than 1, Weyl showed that the sequence Pn is uniformly distributed modulo 1 if the derivative of the polynomial does not belongs to the rational, all of the coefficient of the derivative of polynomial is not rational. In other words, so the given polynomial has at least one non-constant irrational coefficient, then the corresponding sequence going to be uniformly distributed modulo 1. So in particular, if we take p of x equal to alpha x, then we retrieve the first result of Weyl actually. In general, if we take alpha x square in alpha x power k, then we can see that n power k times alpha is uniformly distributed modulo. So all these results proved by something called Weil's criteria. This criteria connects the question about uniform distribution modulo 1 to the question related to bounding certain exponential sum of this kind. So given any sequence xn is uniformly distributed modulo 1 if and only if for every non-zero integer h as limit tends to infinity 1 over n times this particular exponential sum will go to 0. This actually means that for every non-zero integer h, this exponential sum is little over. So order of this exponential sum is like smaller than n, meaning there are lot of cancellation in this particular exponential sum when h for every h not equal to 0. So this criteria is useful calculating so the given sequence is whether uniformly distributed or not. As application of this Weil's criteria, we'll show, we give some examples which are uniformly distributed modulo 1 and which is not uniformly distributed modulo. So in 1948, Vinogradov showed that the sequence of prime, so if we choose any irrational alpha, then Pn alpha is uniformly distributed modulo 1. And we can see that this fractional part of, so if you choose alpha equal to E, then n factorial E is not uniformly distributed. This can be seen from the series expansion of E. In fact, this particular sequence has limit point 0 actually. And log n is not uniformly distributed. This can be shown using Weil's criteria with h equal to 1 case. So h equal to 1 case, this limit is not equal to 0. So the log n is not uniformly distributed. So now we quantify the notion of uniform distribution. So we'll define a notion called discrepancy, which is which actually calculates the rate of convergence of a counting function to the expected limit actually. So we define discrepancy of a given sequence as supremum of all subintervals A close to A open B of 0, 1. So the difference of the counting function by the expected limit. So by definition itself, we can see that uniformly, so the given sequence is uniform distribution modulo 1, if and only if this converges to 0 actually. So, and we can study actually bound of discrepancy. So in case the given sequence is uniformly distributed modulo 1, then we can actually study the bound of, rate of convergence, how fast the counting function converges to the expected limit. So before going to that, we can see some trivial bound for this discrepancy actually. So any given sequence of real numbers, the discrepancy of a sequence bounded above by 1 and bounded below by 1 over n. So bounded above by 1 can be seen from the definition because this is less than 1 actually, and this also subinterval of 0, 1. So this is also less than 1. So difference of both of them in absolute value less than or equal to 1 actually. So, but to see the lower bound, so pick a term, any term from the sequence, say x, and choose epsilon small enough, and consider the interval close to x open x plus epsilon, which actually contains x. So hence the discrepancy is supremum of all such intervals. So this is bigger than or equal to this particular interval. So this particular function, and so actually this interval contains at least x. So this is actually bigger than 1 over n minus epsilon, and epsilon is chosen arbitrarily so that the discrepancy is bounded above by 1 over n. So now, like the statement, this is why we define the notion called discrepancy. So sequence is uniformly distributed modulo 1 if and only if discrepancy is converging to 0. So now recalls the Weil criteria, so which gives some necessary and sufficient condition for uniform distribution modulo 1. And we also want to same kind of expression for the discrepancy actually, like we want to compare the discrepancy with the size of the exponential sum. This was given by Erdos and Turan actually. So this particular theorem calls Erdos-Turan inequality. So if xn be a sequence of real number and for any n bigger than or equal to 1 and any real number h bigger than or equal to 1, the discrepancy of the given sequence is bounded above by 2 over h plus 1 plus 2 times summation h equal to 1 to h 1 over small h times the exponential sum which we had here, absolute value of the exponential sum. So So to calculate the discrepancy, this inequality is very helpful. I mean, because it is just related to calculation of some exponential sum. But calculation of discrepancy often depends on the Diophantine property of a given alpha, actually. So before talking about discrepancy bound, we just define the irrationality measure of a given irrational number, which actually quantifies the irrationality of a given real number. So the irrationality measure mu alpha of a real number alpha is supremum of all real numbers mu, for which this inequality has infinitely many rational solutions. So this actually measures that for any given alpha, so how nicely it has rational, I mean, so it has approximated by the rational number. Actually, this actually measures so that like the behavior of Diophantine approximation of, I mean, this particular alpha, I mean, given alpha. So before stating the discrepancy bound, we just see some properties of this irrationality measure. So by definition, it follows that every rational number has irrationality measure 1. And it follows from the Dirichlet theorem of rational convergence, actually. So that every irrational number has irrationality measure bigger than or equal to 2. And the third one is the theorem due to Ziegel-Rath, actually. So they prove that every algebraic irrational number has irrationality measure 2. So in fact, Kinchin showed that almost all real numbers in the sense of Lebesgue measure has irrationality measure 2. But other numbers also very rich in the real line, in the sense that like we have, in fact, we have like the set of real numbers with irrationality measure is infinity is also dense in R. Like not only dense, I mean, it is also uncountably dense set. So there, like these numbers are called Lioli number or badly approximable number. One such example of such number is this, actually. This number is so decimal expression. So this is actually summation n equal to 1 to infinity 1 over 10 to the power n factorial. See, I mean, so only factorial place there are 1, other places are 0. Factorial to decimal place. So in 2008, N. Bourgeois showed that any given real number tau bigger than 2, the Cantor set contains uncountably many elements with that particular irrationality measure. So it is like, I mean, so Cantor set has measure 0, but still it contains uncountably many elements for any, I mean, with irrationality measure tau for any given real tau bigger than or equal to 2. So with this irrationality notion of irrationality measure and the Erdős-Thurn inequality, we will see the discrepancy bound for some uniformly distributed sequence. So we first study the sequence which we start with, actually. So if alpha is a real number with irrationality measure t plus 1, then the discrepancy of n alpha is bounded above by n to the power minus 1 over t plus epsilon. So observe that if t equal to 1, I mean, the alpha is a real number of irrationality measure 2, which is true for all algebraic irrationals and almost all real numbers. So in that case, it attains the lower bound of discrepancy. That is like when t equal to 1, this is just 1 over n plus, I mean, so 1 over, so n to the power minus 1 plus epsilon, actually. We saw that which is the lower bound of discrepancy. This almost attained the lower bound in that case. So with the same assumption, Benke showed that the fractional, I mean, discrepancy of n square alpha is bounded above by n to the power minus 1 over t plus 1 plus n to the power minus 2 by 5 square root of log n. And Vinogradov showed that, so under same assumption of alpha, I mean, the irrationality measure. So the sequence of prime times alpha, the discrepancy of sequence of primes is bounded above by n to the power minus 1 over 2t plus 2 plus n to the power minus 1 over 5. So in 2018, Mukhopadhyay, Ramare, Vishwanathan, they showed that polynomial values of, so if we take a g of x is a monic real polynomial of degree bigger than or equal to 2, then the corresponding discrepancy is bounded by this number. So now, so this is the classical results. Now we want to see the discrepancy of the further sequence. So before that I'll define then generalized notion of polynomial actually. So polynomial has addition, sum and products in it actually. So we are going to add one more operation with that, so called bracket operation, which is just integral part of the integer. So the generalized polynomial q of x is a real valued function as R obtained from the finite number of real valued polynomials by using the bracket operation sums and products. For example, these are all generalized polynomials. So Green and Toh call these polynomials as bracket polynomials and sequence generated by them as a nil sequences. So in accordance with the Weil's result, one can actually consider uniform distribution of this generalized polynomials also. So this was first considered by many others, for example, Carlson, Veach, Hull, and all these people. So then the discrepancy of the generalized polynomial also studied by Harper and Ramre. So to state their results, we actually require the generalization of irrationality measure for the pairs of real numbers. So which is called finite type actually. So t bigger than or equal to 1 be a real number. We say that a pair alpha comma beta of real numbers is a finite type T if for each epsilon bigger than 0, there is a positive constant which depends on this alpha beta epsilon, only depends on alpha beta epsilon, such that for any pairs of rational integers m non-zero rational integers mn, so this inequality holds. So here this norm actually denotes the distance from x to the nearest integers actually. So similarly, like as analogous to, so we so in the class, so similar to the classical case, we can show that so given any delta gamma comma delta be algebraic numbers such that 1 comma gamma comma delta are linearly independent over rationals, then this number is of finite type 1. And analogous of Kinchin theorem is also true. Almost all pairs of gamma comma delta are of finite type 1. So using under the assumption of type condition on alpha comma alpha beta and beta comma 1 over alpha, Harper and Ramre showed the upper bound of the discrepancy of this generalized polynomial. I mean, in fact, it's just monomial actually. So integral part of n alpha times beta, discrepancy of this sequence is bounded above by -3 times. So n to the power -1 divided by 3t minus 2 plus epsilon actually. And this bound is also nice because when t equal to 1, this actually gives 1 over n. So then later, so Bergelsen et al. Showed the subsequence of that particular sequence is also uniformly distribution along primes actually. So instead of taking all n, if we take set of all primes and consider p alpha integral part beta, then that is also uniformly distributed modulo 1 whenever alpha 1 comma alpha beta are linearly independent over Q. So therefore later we consider so that, like, I mean, studying discrepancy of this particular sequence is also interesting. So we recently considered that problem to see obtain upper bounds for discrepancy of this particular sequence. So then we proved this following theorem under the same assumption of Harper and Ramre, which actually says that alpha comma 1 comma alpha beta is linearly independent over rationals. So then we have the upper bound of discrepancy of this particular sequence. So this is, yeah.
You only considered monomials.
Yes, sir.
But then the Weil's theorem is
True for polynomial, yeah.
So is there such a notion?
Yeah, actually later they, so Anirban, Ramare, Kashi, they showed that particular form of generalized polynomial, G. So g of x is a polynomial with at least one non-constant coefficient is irrational times beta. This kind of polynomials, they actually shown that is also uniformly distributed modulo 1, and they calculated the discrepancy actually. And so recently we are also studying for prime value of this sequence.
That also require that this rationality measure restricted for variables, or is that?
Yeah, that also requires same actually. So in fact, we require irrationality notion for pairs of real numbers. There also, yeah, pairs only. Yeah. So the basic technique is like Fourier approximation of a fractional part function. So that therefore we have like, so in this case we have like two numbers. So that will come. So so alpha and beta. So only that. So the leading coefficient is matter. So other things are, yeah, I think. Yeah, yes.
Yeah.